Okay, then we continue from last time. So last time we have learned a physical quantity called magnetic flux, which the mathematical formula for the magnetic flux is BA cosine theta. B is the magnetic field strength we have been using so far. A is the area of the loop that you're considering, that you're calculating the magnetic flux of the loop, and then you have a cosine theta, where theta is the angle between the normal of the loop and the field lines. So it is like what we did in the topic of light ray, where the angle is defined with respect to the normal. And we found out that mathematically these functions allows us to give an intuitive understanding, which means that the magnetic flux is a measure of the number of field lines enclosed in the loop. So therefore, if you have for example, if you have a larger magnetic flux, it means that the loop you are considering can enclose more magnetic field lines. While if the loop you are considering is parallel to the field lines, it means that its normal is perpendicular to the magnetic field lines, then the loop does not enclose any field lines, so you will have the magnetic flux to be zero. Now, so this is what we call the magnetic flux. Please remember that the intuitive understanding of the magnetic flux is equally important. We do not just really memorize the mathematics, but we also need to have an intuitive understanding. And then because of that, then we could call the magnetic field B as another name called the magnetic flux density, because according to the definition, the magnetic field strength can be written as the magnetic flux divided by an area, and then the magnetic flux divided by area, then we can call this magnetic flux density. The unit of magnetic flux is Weber, so WB, and then divided by the area, which is in meters squared. So therefore we have a new unit of the magnetic flux density. So therefore in a past paper question, sometimes you will see the term magnetic flux density, then you need to know the question is referring to the magnetic field strength B. And then we introduce something called the flux linkage, which is when you consider more than one loop, that physically maybe you have a wires that you make a few number of turns, then the total magnetic flux will be the n, the number of turns, times the magnetic flux of each turn, then the result is called the magnetic flux linkage. So these are the terminologies we need to know for the Faraday's law, and then we write down the Faraday's law as to say the EMF induced in a loop is directly proportional to the rate of change in the magnetic flux linkage. So this is the way we write down the rate of change in magnetic flux linkage. And how do we give an interpretation of this? Is that we try to interpret the right hand side as the gradient of a graph. So that we put here that the EMF induced is the -1 times the gradient of the magnetic flux linkage time graph. This is like the delta y, delta x. This is rise over run. So then we list one example and illustrate that only when there is a change in the magnetic flux linkage, then we will have a EMF induced. And now we do not just say there is an EMF induced, we will also be able to mathematically find out the size of the EMF induced, and then which is the gradient of the corresponding graph. Now, today we will try to extend this idea and then try to apply some very important cases. So there is one classic case that we will need to study. In this case, will be the case that you have a moving conducting rod. In the lesson, we somehow also mentioned this situation when we talk about this topic qualitatively, but now we want to include some quantitative discussions. So what we have now is that we have a region of magnetic field. Let me create a region of magnetic field first. So for simplicity, we always study the case that we only have a uniform magnetic field. So for example, we have a uniform magnetic field which is pointing vertically upward, and we have a plane which is we have a circuit or a coil which is a horizontal. Okay, and then I think maybe even make it even. Need to make it less transparent will be better. Okay, like this. So we have a magnetic field B, or we call it the magnetic flux density B. And then we have a circuit like this, and then the length of the circuit here is L. And what we have is that we have a part which is a conducting rod, which of the length L, and then it is moving at a certain velocity v towards one direction. Now, then in this case, there will be a change in the magnetic flux linkage. First of all, we need to ask, okay, where is the loop? Where the loop is quite obvious will be this part here. This is the corresponding loop that we can study the number of magnetic field lines that it can enclose. So this will be the area that we want to study. The area. Now, as a moving conducting rod, this is like a moving conductor, move to the right hand side, then we will have the loop in yellow enclosing fewer number of field lines. For example, right now it may enclose like around 20 field lines, and then after some times, then this rod will move to here. Therefore, the loop will only of this size only. So therefore, in this case, there is a change in area that leads to a change in magnetic flux linkage. So therefore, qualitatively, our understanding will be when the rod moves, then the area of the loop decreases. Therefore, when you look at the magnetic flux linkage, which is given as N times B times cosine theta, then we will have, well, the N does not change. N is just 1 because there's only one turn. B does not change because the magnetic field is just constant in time. Well, but the area decreases. Well, the theta is also does not change because the normal of the area is still vertical. So therefore, it will just means that it is just parallel. But this is, let's say, the normal. So which is just parallel to the field lines. So we just have the theta equals to 0 all the time. But we have the area decreases, so therefore the A decreases, so therefore the magnetic flux linkage decreases. So by the Faraday's law, we will conclude that there will be a EMF induced. Now we have kind of like discussed this in the lesson, and now we want to make it quantitative. So quantitatively, we look at the equation that EMF is equals to minus and then delta n phi over delta t. Now then we can do some mathematics now. So we have E equals to minus delta, and then we have the phi, the magnetic flux, to be equals to B times A times cosine theta. And then we know that n does not change with time, B does not change with time, and actually cosine theta is just equals to 1 because theta equals to 0. So we have cosine 0 equals to 1. So therefore we can pull out the two factor because they do not change with time. So I have minus n times b. Maybe you can also simplify further because we only have one loop. So n equals to 1. So what we do here is just we simplify the expression, so we have delta BA and then delta T. Now since the magnetic field is constant, we can pull out the magnetic field. Only the area changes with time. So therefore, we keep the delta A in the expression. Now the next question is asked, though I know that this term is not 0 because the rod is moving to the right hand side, therefore the area will change with time. Can we further simplify this term in bracket into something else? Now it turns out that the answer is yes. Now let's consider how to evaluate delta A over delta T. And then we look at the top view of what we are doing. So we have the coil, or we have the circuit like this. And then the length of the circuit is L. And you have a rod which is moving at a velocity V. Now, I want to consider a certain interval of time. So for a time interval, delta t, then this rod will be moved from this place to here. So therefore, there will be a kind of like a movement that the rod will move to make a displacement. And the displacement that it makes will be the speed times the time. T times delta t. So therefore, this will be like the distance traveled by the rod. So it is like after and before. For the time interval of delta t, then this rod will make a displacement of speed times the time. Now then, what is the corresponding change in area for this period of time? Well, the change in area will be this rectangle here. Some book they will use a description to say, first of all, we call this is the delta A, the change in area. Or we will call that this is the area that is swept by the rod. So it's like it's sweeping out a certain area, and this will be the delta A. So with this understanding, delta A can in fact be written as the area of a triangle, which is this length, which is V delta T, times this length, which is L. So therefore, delta A can be written as LV delta T. So everything can be done now. So therefore, the Faraday's law, we have E equals to minus B delta A over delta T. So let's repeat it here. And delta A is equals to VL delta T. So therefore, we have minus B VL delta T by substitution. and then divided by delta t. And therefore, these two delta t cancel. So therefore, at the end, our EMF is equal to minus BVL. If we just consider magnitude, we could ignore the minus sign. EMF is equals to BVL in magnitude. So this is the equation as the EMF induced by rod. When this rod is in a magnetic flux density B, assumed to be uniform, and when a rod is moving at a velocity v, with the length L of the rod. There is some assumption, of course. For example, we have assumed that the rod is moving, or the velocity of the rod is perpendicular to the direction of the magnetic flux density. Also, there is an assumption that the magnetic flux density is uniform. There are many assumptions. B is uniform, and also the case that we have assumed that V is perpendicular to B in this case. But that is usually the situation on the setup that we will be tested in examination. So therefore, it means that we have this setup accompany this equation. So when this rod is moving to the right hand side, then there will be EMF induced. Well, the same thing should also happen if the rod is moving to the left. It will not affect the magnitude of the EMF induced. But I want you to pay attention to the fact that in this equation, actually it does not include any factors related to this length of the conductor. In other words, even I could delete this part of the circuit and just let a rod, an isolated rod, which is not connected in any way, and it just move in a region with a magnetic field. In this case, EMF will also be induced, and it still be given by the magnetic flux density times the speed or the velocity and times the length of the rod. That it will not be necessary for this rod to be connected in a closed circuit. That EMF will still be induced in this case. Well, without any closed circuit, we cannot say anything about the loop, but we could say, using the interpretation we have before, because it is cutting the magnetic field lines. Therefore, everything is still okay. But the only difference is, if the rod is just isolated, that it is not connected to any closed circuit, then what you will have is just you will only have EMF induced, but you will not able to allow this induced EMF to give rise to a induced current because the circuit is not closed. Okay. But no current. Okay. So this is one key result that in your examination they like to test. When they are talking about just an isolated rod moving in a magnetic field, then the EMF induced is given by this formula. This is a special case. This is unlike the general case we have for the Faraday's law, which can be applied to all cases. But for examination purpose, this is actually a quite common questions that you can find. Let me see if I can find a question. To elaborate this further. Still loading. EM induction. I think due to the copyright, I don't want to upload the question here. I can print a hard copy to you when we get back to the school, but I don't want to show it here. Now, let me see. I think I give this question to you in the only unlike this. Yeah. So for example, so you're given a resistor R, and it's called X and Y for these two directions, and this is on the length D. And then this is like this situation, and then you are in the D region, that you have a uniform magnetic field which is pointing into the page. So this region has a magnetic field B going into the page, and then you have a rod PQ, and this is like means the magnetic field is going into the page, into, and then PQ, and then it is, this length is L, so it is a bit longer than the length here, like this. Okay, and then it's moving with velocity v. And now what they want to ask is to ask about first of all the magnitude of the current induced in this circuit, and then the second one is about the direction. Is it going from X to Y, or from Y to X? Now from the equation we have just learned already, just now, we will have the EMF induced is equals to BLV. But this L may not be this L. Because you need to remember, during the proof, this L here denotes not the length of the conducting rod, but only of this part. That means only on this part. No matter how long the extra part of the rod is, the actual area concerned is only this region. So therefore, they intentionally confuse you. So therefore, for the substitution, we can use the B they use, but we should actually use D in the questions. So this is like in general, we call it BLI, BLV, but in this question, the length we should use should be D. And then times the V, that's okay. So now we have this. And how to find the current? We have V equals to IR, so EMF over the resistance R. So therefore the magnitude of the current induced will be just equals to B dV over R. Now then, how about the direction? In order to deal with the direction, we need to use the Lenz's law. So this is something we cover in the lesson. The Lenz's law will tells you that the direction of the current will try to oppose the changes that causes it. So in this case, the changes is the motion of the rod PQ. So we can just 50-50, well, try to make a guess. For example, if the current is flowing here, then you can use the Fermi-Stephan rule to deduce what should be the direction of the magnetic force. And then see if it obeys the Lenz's law. So this is usually what I did. So I will first pretend that I have an answers. But the answers is not answer. Answers is a guess. So pretend that we have an answers that the current is going here. Then you can use the Fermi-Stephan rule. Then you can find out that if this is the direction of the current, then the force will be going to the left. Force going to the left is good because in this case, the force opposes the velocity. So therefore, it means it obeys Lenz's law. So therefore, that's the answer. The current will flow from Q to P and then X to Y. So therefore, the answer is from X to Y. Okay? Now just in case this time you're not that lucky, I did not pretend, I did not choose the answers to be this direction. Maybe I choose the opposite direction. Then the force will be, maybe I choose this. If I this time I choose the current like this, then I found that the force will go this way then. Then that means the force will be parallel to velocity. So therefore, it opposes. That means it's not opposing the change, that it's actually reinforced the change. That means it's not good. Then therefore you know the direction of the current should be opposite to this. Okay, I think, yeah, to do some detailed discussion about this kind of situation. Now, okay, then the next thing will be, we look at the case about, let me see. I look at the case about the rotating rod. This is another classic case. What's the classic case do? Classic case 2 is like the AC generator. So we have N, we have S. These are the two poles, and then we have some magnetic field lines pointing from north to south. And then in between we have a coil, and the coil, to consider only one coil, or you can actually consider a few coil, then we will just have N bigger than 1. But anyway, to simplify things, we'll just consider a coil like this. And then externally, then this will be connected to like a slip ring, and then like this, and then it will connect it to the external circuit. So I will connect to a resistor, for example. So here, this part is only connected to this, and this is like connected to this part. Maybe it's poor joint. So we have one ring here, and then this is connected to this part, and this one is connected through to this part here. This is another coil. This we just connect to here with this. Okay, so well, first of all, to recap what we have learned, just understand this question qualitatively first without any doing calculation. So qualitatively, we know that there will be a cutting of magnetic field lines. Therefore, there must be EMF induced. So now what we want to ask is, can we write down an expression for the EMF induced in this case? Well, then we need to do a quantitative analysis here. Now, quantitatively, this part is really not easy to understand. We need to first look at really what part of magnetic flux linkage is being changed. So we look at the magnetic flux linkage, which is N phi equals to NBA cosine theta. You found that in this case, actually N, no change. B, also no change. Well, the area A is also no change. So therefore, they are all constant. So the only thing that has been changed is just the theta. If you recap what is a theta, theta is the angle between the normal and the magnetic field. When someone rotates this coil, then this normal will change into different directions. So the angle between the normal and the magnetic field will be changing. So therefore, it is actually the theta that varies with time. And how theta varies with time? We go back to what we have learned in circular motion. We define this as the angular velocity times the time. So this is maybe need sometimes to recap. Omega is the angular velocity in the unit of radian per second. Effectively, it is telling you the rate of change of angular displacement. So therefore, this is just like velocity. If you already forgot what you have learned in circular motion, this is like the distance travel, and this is like the velocity. So velocity times time, that will be the displacement. But now we are not looking at how many meters that it travels. We are looking at how many degrees or how many radians that it makes. Therefore, we have the angular velocity multiplied by time. Now, then we can use the Faraday's law. EMF is equal to minus change in N phi over change in time. So therefore, we have minus change in NBA cosine omega t dt. Then we have, because NBA are constant, we can just pull it out. Then we have this. Now, the interesting part here is, in order for us to evaluate this, actually we need calculus. From calculus, use another color. For calculus, the result here will be equal to minus omega sine omega t. So therefore, putting everything together, then we will have a EMF equals to NBA omega sine omega t. This will be the expression we use for the EMF induced in a turning coil. Well, EMF induced in volts, N is the number of turns in the coil, B is the magnetic flux, density, A is the area of the loop of the coil, and the omega is the angular velocity. So there is a sine theta here to give you a understanding of how it changes with time. So there's one thing particularly we are interested in is that means the EMF is actually a function of time, which kind of makes sense because it actually does not really cut the magnetic field lines in the same way over time. So for example, it will first start from 0 and then like this, and then like this, like this, this, like this, like this. Now the key point I want you to remember is you need to know the maximum EMF induced. That is determined by NBA omega. So that means if you have a larger number of turns, stronger magnetic field strength, and larger area, and you spin the coil faster at a faster rate, then you will have a larger EMF induced. Well, this is like the vertical scales telling you how high the EMF can be, while the horizontal scales will tell you like how fast the EMF fluctuates or varies. Then this part here, you remember, it's just the period t, and this is equals to 2 pi over omega. This is what we have learned in the topic of circular motion. Okay, so this will be the classic case number 2, which is about the turning of the coil in a uniform magnetic field. There are some special cases that we want to pay attention to as well, like exactly when will the EMF be 0, or like when will the EMF be maximized. This will be something we will talk about in next time. But there are like 4 pages already, and I want to end it here.